Howdy, howdy. This is Mr. Potter. What we're going to do in section 6.4 is we're going to talk about differential equations. We're going to talk about exponential growth, and we're going to talk about how to solve exponential equations using the anti-differentiation techniques that we've discussed in this chapter. So we're going to start first with the idea of exponential growth. So let's say that I'm starting off at a particular time, t equals 0, and I've got 1,000 bacteria. And after an hour, my 1,000 bacteria are going to double. So at t equals 1, my bacteria now becomes 2,000 bacteria. And if those 2,000 bacteria double again the next hour, at t equals 2, we have 4,000 bacteria. And at t equals 3 hours, we end up with 8,000 bacteria. And at t equals 4 hours, we have 16,000 bacteria. Now I know that some of this bacteria is going to die, but this idea of exponential growth is one of the reasons why you can go to bed feeling perfectly healthy and wake up the next morning and you have a terrible throat ache, or you have a terrible headache. It's because of this exponential growth that those situations happen. And what's happening in this exponential growth situation is that the change in bacteria, let's call that dy dt, the change in the bacteria depends not on time, but it depends on the number of bacteria. From t equals 0 to t equals 1, the change in bacteria is 1,000. From t equals 1 to t equals 2, the change in bacteria is 2,000. And so if I have y bacteria at a particular time, the next hour I'm going to have twice as much bacteria. In other words, my rate of change is really going to be equal to y. And so this is what we call our exponential growth. Differential equation. So this equation represents differential growth. So what we want to do is we want to talk about how do we go about solving this? Because right now this is a differential equation, but ideally I would want to have an explicit function for my growth. And this exponential growth should be a hint as to what we're going to be ending up with. So I want to talk about how we actually go about solving a differential equation. There's actually a 5-step process for this. So the very first thing that I want to do is I want to separate my variables. So for the equation that we have dy dx, or dy dt equals y. And the whole idea is that my initial population in this case is 1,000 bacteria. So I want to separate these variables. I want to get all of my y terms on one side, and I want to get all my t terms on the other side. So the first thing I'm going to do is move my differential over to the right side. So I end up with dy equals y dt. But now I have mixed variables over here, and I want to move this y over to the other side. So this really becomes 1 over y dy equals dt. So that's my first step, is to separate my variables. The second thing that I want to do is I want to get rid of the differential part. And in order to get rid of this dy, we actually need to find the antiderivative. Remember that the antiderivative, the integral symbol, is my left parentheses, and the differential dy or dt is my right parentheses. So what I want to do is I want to integrate both sides. And so that's what I'm going to do here. I'm going to take the integral of 1 over y dy equals the integral of dt. And I know that these functions should be equal as long as I take into consideration that constant. I know that the antiderivative of 1 over y is the natural log of the absolute value of y plus some constant. And I know that the integral of 1 dt is t plus a different constant. So I really have two different constants here. But what's really going to be helpful is if I put my constant with the independent variable. So I really want my constant to be over here with the c. So I've got the natural log of the absolute value of y equals t plus c. And notice I don't have a prefix like c1 or c2. This is just c. Now, right now, I know that for this initial condition, I don't really need to worry about the absolute value here, because I'm only going to be dealing with positive bacteria. My bacteria is a model that I'm trying to write an equation for, and so I'll never have a negative number. But I will have to talk about domain, and we'll do that in our last example today. The fourth thing that I want to do is I need to solve for my dependent variable. I need to solve for y. So I need to figure out what y is equal to. And I know that I can get rid of natural log by taking the exponential of both sides. And that should be equal to e to the t plus c power. So here, exponentials and logarithms get rid of each other, leaving us with just a y. And over here, I'm going to have e to the t plus c power. But what I also know is that when I'm adding exponents, I'm really multiplying terms together. So I really have e to the t times e to the c. And because e to the c is a constant, this is really some constant times e to the t that y is equal to. So I've got y equals k e to the t, where k is just this e to the c. K is just some constant of growth. And the last thing that I want to do, step 5, is I want to solve for my constant. I'm going to be using the initial conditions that we had. This idea here that y of 0 equals 1,000, so when t equals 0, y equals 1,000, and my equation becomes 1,000 equals k times e to the 0 power. And of course, e to the 0 is 1. So I really have k times 1 equals 1,000. And so k ends up being equal to 1,000. So my solution to this differential equation is going to be y equals 1,000 e to the t power. This incorporates my constant. This incorporates my initial growth. And if I wanted to check, the derivative of this is going to be 1,000 times the derivative of an exponential, which is my exponential. Notice that y prime in this case really and truly is equal to y. So these 5 steps are how we need to solve a differential equation. The very first thing that I had to do was to separate my variables. And so instead of having dy dt, I had a differential dy and everything dealing with y on one side, and a differential dt and everything dealing with t on the other side. Once I separated my variables, I want to get rid of my differentials, so I integrate both sides. So this idea of the integral to get rid of my differential dy and an integral here to get rid of my differential dt gives me one function equals another function with constants of integration on both sides. And I resolve that by putting my constant on the independent variable side. This is really part of the idea of solving for my dependent variable. But putting my constant on the independent variable side helps me to get my variable by itself. I need to solve for my dependent variable, so I had to get y by itself, y as a function of t. The idea is that instead of having a relation, I want a function. And then finally, I need to make sure that I satisfy these initial conditions. I need to make sure that my equation models the situation that I'm interested in. And in solving for k, I end up with the true solution to our differential equation. So I want to go through a couple more examples of this. So let's start off with this differential equation. Let's say that I have dy dx is equal to y squared times x squared. And I know that it passes through the point 1, 4. So the first thing that I need to do is I need to separate these differential equations. So I'm going to get all my differentials on opposite sides. dy equals y squared x squared dx. And I need to move y squared to the other side. So I really have 1 over y squared dy equals x squared dx. And some people may like to see this written as y to the negative 2, because it's going to make this next step easier. Remember, my second step is to take the antiderivative of both sides. And so in doing that, I'm going to have to use the power rule for each of these polynomials. I'm going to end up with y to the negative 1 divided by negative 1 equals the antiderivative of this, which would be x cubed over 3. And I'm not going to put c1 and c2. I'm going to leap immediately to my step 3, where I put my constant on the independent variable side. Step 4 is I need to get y by itself. If I want to actually write this as a function instead of just a relation. So first thing I'm going to do is multiply both sides by -1. So y to the -1 power equals negative x cubed over 3 plus a constant. Now I say plus a constant instead of a minus a constant because -1 times a constant is actually going to give me a constant value. And rather than just litter this thing with all these different letters, I know that C is the constant that I'm going to be working with if it's being added or subtracted. Now this is y to the -1, so if I really want to find out what y is, I need to take the reciprocal of both sides. So I have 1 over -1/3 x cubed plus a constant. So this is my differential equation solution. And I need to finish it by taking a look at these initial conditions. The idea is that when x is 1, y is 4. So I'm going to have 4 equals 1 over -1/3 x cubed plus a constant. Now I'm going to solve for c. So I've got 1/4 here, and if I take the reciprocal, and of course taking the reciprocal here just gives me my denominator, -1/3 plus a constant, and I can add 1/3 to this side, so I end up with 1/4 plus 1/3 is my constant, which in this case would be 7/12. And so my differential equation has the solution y equals 1 over -1/3 x cubed plus 7/12. So I have a solution for my differential equation, and if I really wanted to, I could check this. I could see if I take the derivative and then multiply times y squared times x squared, do I get the same thing on both sides? I'm not going to do that right now. But really the whole idea is these 5 steps that we've talked about. Step 1 is separating our differential. We had dy and dx, and getting all the like variables on opposite sides. Step 2 was to get rid of the differentials by integrating both sides. And when I do that, I end up with a constant of integration, which I want to put on the independent variable side. At this point, I want to solve for my function. I want to have y as a function of f of x. And then the last thing I want to do is I want to take these initial conditions, my initial x and my initial y, substitute in and actually solve for c. So I end up with a solution to my differential equation. I want to do one more example. And so what I'm going to do is I'm going to come up with this equation, differential equation here. I've got dy dx is equal to x over y. And I'm telling you that it passes through the point 1, 1. Actually, let's make it 1, negative 1, because I said I would be talking about how the domain could affect my differential equation. So again, step 1 is to separate my variables. I'm going to multiply both sides by y and multiply both sides by dx. So I end up with y dy equals x dx. My second step is to take the antiderivative of both sides. And that's going to give me y squared over 2 equals x squared over 2. My step 3 is to make sure I deal with my constant of integration. I put it with my independent variable. And now I want to solve for y. And this is where we end up with the situation where we have to be aware of our domain. Multiplying both sides by 2 gives me y squared equals x squared plus 2 times a constant is constant. And when I take the square root, I end up with y equals plus or minus the square root of x squared plus c. And I'm noticing that for my initial values, y is negative 1. So I really want to deal with y equals negative radical x squared plus c. And so what I need to do now is I need to substitute these x and y coordinates into my function and solve for c. So I end up with 1 equals negative radical of 1 squared plus c, or negative 1. So negative 1 equals negative radical 1 plus c. And I can square both sides, and I get 1 equals 1 plus c. And so c in this case must be 0. And so my function ends up being y equals negative radical x squared, or another way to write that would be the negative absolute value of x. And so my graph for this differential equation would look something like this. My absolute value of x just reflected across the x-axis. And notice that my differential equation is undefined when y equals 0. When y equals 0, that's this point here. So I see that my graph that I've got here actually satisfies my differential equation as well. This five-step process is what we're really interested in, because on the AP exam, on the free response section, you'll be asked to find a solution to a differential equation. And this five-step process is also indicative of where the 5 points come from that you would get for solving a differential equation. A first point for separating the variables, a second point for finding the antiderivative, a third point for making sure you deal with that constant of integration, a fourth point for solving explicitly for y, and a fifth point for solving for your constant of integration. And of course, we're going to have to make sure that we take care of our domain as well. The thing is, in this case, our range deals with this -1, and so I need to make sure that I'm dealing with the negative root for my differential equation. This five-step process is very important, and it's something that students need to be very comfortable with. As we've said with all the things we've talked about in this particular chapter, practice is most important. The only way to get good at this is to repeat it and repeat it and repeat it. So, this is Mr. Potter. Thank you for watching. Have a great day.